Welcome to monthly Lithuanian AI Association meetup. And today we have two exciting topics, which is NLP. We talk about NLP applications and sensor data fusion. So let me briefly introduce myself. My name is Davidas. I am data scientist at IBM. And from this month, I am organizer of Artificial Intelligence Association of Lithuania, these monthly meetups. So Dovydas give me opportunity to be in charge of these meetups, and I'm really thankful for him. And if you have some ideas or speakers who you want to hear in the future meetups, just write me on Slack or on my LinkedIn page. So what we are talking today, I give you briefly talk about our community updates. We have a couple of exciting news. Then Vilija Kodita talk about education to skill mapping using hierarchical classification and transformer neural networks. After Vilja's talk, Danny Bushman talk about visual and radar sensor fusion. And after these two presentations, we have a Q&A session. So we don't have like Q&A session after each presentation, but we have like both question answering session after both presentations. So community updates. As I say, I have one exciting news, which you should be hurry. On the Thursday, we have Lithuanian AI Association non-formal meetup, which if you want to meet our association members in the live event, talk about like from industry professionals and people from academia who is all association members, you should need be in this meetup. So one of the thing that we have like very limited people who can attend. So we prepared this registration form, and this form you can find on our Slack channels, on both Slack channels, and you should be registered until tomorrow morning. We also have registration forms on our LinkedIn page and Facebook. So you should be hurry because we have like limited amount of seats in this meetup, and we are preparing like all the programs and fun things for meetup attendees. And the second news, like not the new news, but we also presenting this like previous month, is that we have dedicated Slack for our members. So right now we have like two Slack channels. One is for general AI community of Lithuania, and the second one only Artificial Intelligence Association of Lithuania members, which we have a lot of different, which we like have channels with different news and other interesting things which is associated with our association. Okay, so let's start with like our first talk. So I want to present you Vilija Kodita, data analyst at Government Strategic Analysis Center, and her talk, Education to Skill Mapping using Hierarchical Classification and Transformers Neural Network. So Vilija, when you are ready, I'm stopping sharing my screen, and you should.
Thank you, Davidas.
Yeah.
Okay. Can you see my slides?
Yes.
Thank you. So hello, everyone. I am Vilija, and today I will present model that maps education to skill. And this model was created using hierarchical classification and transformer neural network. This model is described in a recently published article, which is open access, and if you are interested, you can check it out. And there are two circumstances that allowed us to build this model. First circumstance is that I'm working in an organization called Strata, and this organization provides information based on data and expertise for the strategic questions. And this information is given to government and ministries. Myself, I'm working as a data analyst on the human resource forecast project. And with our team, we experimenting with different methodologies and looking at the most promising in order to produce our forecasts. And the second circumstance is that this year I graduated with a master's degree in data science. And this model actually was as my master thesis project, and university helped me with methodological advice and supervision. So in this presentation, I will first talk about relevance of the topic, why education and occupation and relationship between them is important for national policy. Then I will talk about model, how we created this model, and I will present in a final slides how it's possible to apply this model in practice. So to begin with, there are many areas where knowledge about relationship between education and occupation can be used. First of all, it's for practical applications as a vocational guidance for graduates of schools, because it's important that they could make informed decision about their future studies, and knowledge about how graduates of different education programs succeeding in job market is important to form this informed decision. And also knowledge about how successful graduates of different education programs is important for guidance for education institutions as well. Second area is aspect that this information, it can be used for further data analysis, for instance, for human resource forecasting, or different scenarios generation exercise. And finally, more broadly speaking, information about how education converts to occupations is important for the larger political questions, such as lifelong learning strategy or skill shortage management policies. So speaking more specifically, knowledge about relationship between education and occupation are important in answering very practical and specific questions, such as what occupation will graduates from certain education program most likely acquire, or if we have a newly created program, where those graduates most likely will work in the future. Also, if we are thinking about skill shortage, knowledge about education and occupation can answer such a questions of which education programs will produce professionals that are currently in short supply, or what kind of graduates from other education programs could be additionally trained, that they could be redeployed into this shortage occupations. And then also more long-term questions: how occupational profile will change if we will add additional skill sets to our education programs, for instance, digital skills, or how to transition, how we should change education programs in order to transition to high value-added economy. And those questions are very complex and requires complex solutions, but they all are united by this common denominator of relationship education between education and occupation. So our aim was to create a model that would predict most likely occupations from the completed education programs, from this information about completed education programs. And we not only wanted to create such a model that would predict accurately enough, but would have some nice, interesting application features. We also used national level data to experiment with our model. Namely, we used educational information of residents and their occupational data. But administrative data also have its own perks. And if we want to use educational information as input, and if we want to use solely information all on education program as a dummy variable, we have some certain problems. For instance, there is a large number of such education programs, and this list is constantly changing, sometimes on a daily basis. Sometimes some programs are canceled, new programs are created, or some programs are modified. And for instance, it's impossible to map a new education program to occupation because there is no historical data about it, or because programs are short-lived. There are very few graduates of that program. And additionally, residents might have more than one might complete more than one education program. So in combination, their educational background might result in a unique set of skills, and it's quite difficult to predict most likely occupation. So to sum up, for the input, if we would use separate education program as dummy variables, we would have highly sparse input data, and it's not very practical. So in order to solve those problems, instead of using education programs as dummy variables, we used description of a program. And in order to create our model, we transformed this description into text embeddings. And for that, we used BERT. So speaking simply, when we are transforming our text to text embeddings, we are transforming education program description into vector, and this is our input data. from our output side, when we have occupations, we also have some challenges or opportunities, because in administrative data, we have occupations labeled using international standard occupation classification. And this classification in itself has a hierarchical structure. And we use this hierarchical structure and created hierarchical classifier for our output. And this partially solved the problem of administrative data, because we have quite big class imbalance. Some occupations are occupied by very few graduates, and some occupations have very large number of cases. So this creates imbalanced classes and creates additional challenges to train our model. For higher level of hierarchical classifier, we have more precise predictions, because the groups are larger and this imbalance is not that important. So to sum up, we had several challenges of administrative data that we solved with additional elements of model. So as it was mentioned before, we had sparse input data, which we transformed using educational program descriptions and by using text embeddings. For the output, we had class imbalance, and we solved this with a hierarchical classifier and added additional specific loss function, which is called focal loss, and it's usually used in computer vision models. Also, there was some features of the data, but for the output, we had many classes and multiple cases, because graduates sometimes at the same time have more than one job. So for that, we used multi-label classifier. And keeping in mind all these elements, we created 6 models that were tested. So first of all, we created baseline model, and we added those additional elements that I was naming before to the intermediate models. And our last final model took the best elements of intermediate models with the best parameters. So our final model included text input, which was transformed with BERT into text embeddings. And we use hierarchical classifier. And that's how we achieved our final model. And so about applications, I have some examples to show. First of all, what we wanted to see if our model predicts well in comparison with a real data set. So we compare how our final model, given text input, predicts most likely occupations, and if this coincides with a real data set, with the real occupational frequencies of a certain program graduates. So here you see the example of pedagogy program, and we see that predicted occupations coincides with a real data set, with the top most frequent occupations. Another example, we also tested if our model performs well when we try to predict most likely occupation for several education programs. So here you see an example of informatics studies. The first is only bachelor degree in informatics. Second example is informatics, two education programs in informatics is a bachelor and master degree. And third example is mixed education of informatics and music performance. So we see in all those three cases that we have quite similar occupations. Yet in the third case, those occupations have smaller probabilities, but this is logic, because in real data set, you can see that graduates of informatics studies usually work as IT professionals. So this coincides with historical data. Third example of application is a prediction for new education program. And here we provide with example of a newly created education program of artificial intelligence in KTU. So we took the description of this program and predicted most likely occupations that are related with informatics. And this program at the moment of model creation didn't have any graduates yet. One more example of application is a prediction after program description alteration. And here we see the example of welder training program. And we slightly modified this welder training program description, adding additional digital skill set. And we can see that in both cases, predicted occupations are related to welding. Yet for the second case, there are more occupations related with electronics because of this digital skills added. Well, and the last example, how perhaps it's possible to use this model is occupational similarity search. Here we took a bottleneck layer of a model. It's one but the last layer. And we mapped it, those education programs according to their occupational similarity. And based on assumption that education programs that are closer have similar skill set, we can analyze nearest education programs to try to deal, for instance, with occupational shortage. Okay, so this is all what I wanted to present today, and thank you very much for your attention.
Thank you very much, Vilija. Super interesting topic about education, and I think you get 10 from your master, yes?
Yes.
Yeah. So if you have a question for Vilija, you can write on our YouTube live session. We have like the chat, and we answer all these questions after second our second topic. And I want to present you Danny Butcher, which is which we want to present you today, which is Vice President and of R&D and OCAP. Yeah. Thank you very much, Danny. And his topic is visual and radar sensor fusion. So Danny, if you're ready, I stop sharing my screen and stage is yours.
Just a second. Hello. So hello. I will thank you for this opportunity to present some work that I've been doing for the last few years. It's about visual and radar sensor fusion. So a little bit about me. My name is Danny Buchman. I'm a VP R&D of GAL. We are an electro-optic company, and we are developing systems that uses thermal imaging and analytics for few applications such as gas detection, in border protection, and perimeter security, and aviation for advanced vision systems. This work was mostly done in my previous company that I was their CEO, and the research was dealing with fusion between the radars and the daylight cameras. So it's kind of mixture of the things. So in general, today we have a lot of the fusion itself of radar and image become quite popular these days, and it's used in a lot of applications such as advanced driver systems, autonomous cars, healthcare and remote monitoring for healthcare, security and other applications, as most of the research and the work was done for perimeter security. So I can today in border protection or perimeter security, there is a lot of usage of radar and imaging, but most of the imaging done with pan-tilt systems. The pan-tilts, in that case, the radar doing detections, and we are doing classifications and intruder investigation by cameras with moving of pan-tilt, and also we are performing some kind of tracking, split of the track between the radars and the image systems. What we performed is the close integration between the radars and the imaging, so the imager or video systems can constantly absorb the same terrain as the radar. In that case, we can perform full image fusion like it's done in the other applications. So what is the motive of that things? And so it's not only used for perimeter protection, it's also used for cars and other applications. I think the basic idea to start using such approach for perimeter security came from car and advanced driver system. So here you can see the table that advantage and disadvantage about cameras and radars. So we can see that trajectory movement it's hard to detect by radar. The perpendicular targets are hard to detect by camera. the camera has higher resolution, as we can see. Of course, the radar has lower angular resolution, but radar detects distance. We cannot see colors from the radars, but we can do radars 4D, so we can estimate motion part from the humans. There is also redundancy of information. So if the detection done by radar, you cannot say if it's actually human, car, or animal. Although I will touch it in the future on the presentation. And you have more than one source of information to provide. Here is some link. I will show it later. Some short presentation or short movie that presents the advantage of fusion for the car usage. So what is the video? Starting from the video, what is the video detection? So video counts as the presentation of matrix, of two-dimensional matrix for single image, and it's built from R, G, and B. This is the colors, red, green, and blue colors for each pixel, and the resolution is described as the size of the matrix. So you can see if it's the single frame has three matrices. It's RGB presentation for each pixel, and with the time we have capturing images. The most of the cameras work from 25 Hz, so with 25 frames per second. There is higher frequency cameras or low frequency cameras, but all the cameras capture the image, the single image, and then translate it in time domain. We are from that part, we are going to do object detection, moving object detection, and object tracking. So from the single image, we can detect the single shot detection and single shot classification. Okay, and tell if the image has tree, has human, has car, chair, whatever. As long as we train the network for that, we can detect moving object on few frames, and to be able to track the object, we need to have the correlation between different frames, so we can track. Okay. There are some basic principles of moving object detections that come with background subtraction. So we need to decide what is the background and what is the actual moving object. This thing is running some filters on the frames, and then we generate the background or reference frame and doing the division of the frames. Not necessary information. Temporary difference, we subscribe for each pixel and looking for a difference of each pixel. And another approach is the optical flow calculation. The radar data, there is few representation for radar data. I think one of them is pretty useful. One of the radar data generates frame with targets, with detected targets. Most of the targets detected by radar after translation, they are points in in 3 dimensions that have velocity and have angle and have the distance to the target. And we receiving for each frame of the radar, for each scan of the radar, we received the target list. The target list needs to be translated, and we need to understand if the target is real or not real, and if it's moving or not moving. Sometimes there are ghosts generated by in the radar field, and sometimes there are objects that generates pure points. So we need to clear it, and we need to have a tracker that can detect the real targets and not. What to have to say all that together? So as described, we have the video source. Each frame came to 3 algorithms. One algorithm is a motion detector algorithm, as described, and we have generated tracks from motion detector algorithm. We have image classification that from each image what we receive, we classify the targets, and we have placed in the image that there is classified targets there. We have radar source that generates point cloud, and from the point line we generate tracks. Each track is already pure track, and we actually can generate triggers or alarms from each of them separately. The fusion scheme gives build with Kalman based on Kalman filter, and generates the detection according to 3 classical to 3 inputs. Actually, I will describe 4 inputs for the fusion scheme. Another thing that we can generate from the radar source just before the point cloud itself. We can also do the classification of the object and train it like an image. So the fusion scheme based build with Kalman filtering has the possibility to detect and track common tracks from 3 sources, and generates the single alarm with higher probability of detection and lower noise or false alarm. And what we have used for image classification, we have used YOLO P3 version, that it is come out of the box pre-trained network, and it is very popular for image processing today. And this is convolutional neural network that have multiple layers with scale down and fully connected layers, or yes, fully connected layers with that can have that pre-trained for 1,000 types of images. Actually, what we did, we ran this. We trained we added training to this network according to images that we received from our cameras, because to enable more accurate detections. The second part of this is the VND model. So as I told, there is a background subtraction. We have morphological of operations such as erosion and deletion, blob detection and filtering of the blobs, And after that, we perform a tracking. The tracking itself is based on Kalman filter tracking. So there is previous state and current state, and there is a calculation for the next state. And prediction of where the next target will be. It enables better performance of the tracking itself. In addition to tracker, we have additional sources for the detection, and also we have scaling mask and region of interest mask. So to enable to reduce the tracking itself. The configuration is the speeds and the size of the targets available, and other parameters that are relative for the detections. And of course, the next step is, as I said, video analytics itself, such as movement to left, right, a few targets moving together, or a region of interest that are used to generate tracks before going to few tracks. Radar tracking. To the same, we are building the model of the clutter, and after the receiving the point cloud, we are matching the data, the previous and the current data, generating the targets, and we have matched track vectors that are going to the same principle of tracking with Kalman filtering, and the output is radar tracks. This is something that was actually we can do pretty same approach to the radar, as long as we don't use only point cloud. We can use the real signals, and actually the data received after FFT, it is very close to the image. So what we see, so this is transferred data from FFT for each target, and it looks like some noisy image. But if we will look closely, we can see the center is the velocity. It is Doppler velocity of the target, and there is smooth changes from that. There is, let's say, if you look on some human, the most of the motion is the main body velocity, but the hands and let's say legs, generates another small difference inside this velocity. So so this is shown and generated here, and we have additional motions that is not main Doppler velocity. From that we can train the network, and we can describe if it's a human or animal or another. So actually what we did, we received pretty big data set of images or according to recording from the radars, according to the geolocation, sensors, days, tracks, and segments, and these segments were marked with human, no detection, and animal. We have trained two neural networks. One is ResNet based, and another one ResNet like, just a bit smaller, and have trained it for different parameters and actually succeeded to get detection and separation between the animals and humans. There is also possible, we didn't have, because of lack of data, we didn't have another things like cars inside, so we could generate kind of database that can be used in addition to here as an addition to fusion scheme and as already detected and classified objects from the radar. And of course, the fusion scheme will be bigger than that. So in this competition, we have got for the on top 10 in the competition of detecting animals and humans from the radar raw signaling. And for public test, we got 95% of detection, and the private test, we got 85% of the detections. And actually finished on top 10 in this competition. I think that's all for me about the work and the radar fusion with the images. Thank you, and if you have the questions, then you ask. I will please ask, and then we'll back on.
Yeah, thank you very much, Danny. Yeah, we have a couple of questions for both our speakers. Just a minute. Share my screen. So first question is for Vilja. So it's question from Linus. Great presentation. My question, can you elaborate on possible applications for creating ideal study program which produce a student for preferable profession?
Well, I don't think that this model is suitable for exactly this task, because perhaps when you are creating this perfect program, you are taking into account other aspects. For instance, if you have lecturers who are able to give lectures. So this model, I believe, is more suitable just to evaluate after this study program is formed, to evaluate most likely occupations.
Okay, so we have also second question from Daniel. What if similar or related programs would be collected into groups?
I'm not sure I understand question, but I think that maybe this question is related with this sparse input data, and the question is about what if we use not text embeddings but larger groups of education programs as an input. So this is possible, and I was trying out this approach. It's not very accurate, and it don't have this practical applications like possibility to modify description, adding some additional skills. But this approach could also perhaps work.
Okay, thank you very much. We have also a couple of, so Daniel also right, I mean those where data is sparse. Okay. So you answer, yeah.
Yeah, I think I answered.
Yeah, okay, thank you. So we have also a couple questions from Linus for you, Danny. So first question is, what approaches are used for not forgot the intersecting or crossing moving target?
So what we are using to select the targets and actually track the targets is the Kalman filtering approach with probability filtering. Okay. Sorry, the probability filter uses the Kalman approach. Okay, so it estimates the previous state, the cluster state, and the next state of the moving target, and dealing with the probability of detection and actually target accuracy on such point. Okay, so this is what's done for the tracking.
Okay, thank you. So the second question also from Linus, is it impossible to add realistic data augmentation to transform images to represent realistic noises and unexpected situations in raw sensor data?
Let's say we didn't. I think we can generate and train with additional images. So there is an approach. Then you don't have a data. You can add additional data into images, noise, and also the targets. Okay, for training. So I believe so. Yes, and we have tried such approach. The issue that can come that the model will adapt to your training, and this is one of the things you need to be aware of, that actually generated data still is generated. It's not random. It's not only random, so we the model can adapt to it. But yes, when we have lack of data, you are using data that we can generate.
Yeah, thank you very much, Danny. So I think we don't have any other questions. So I think we can finish here today. So thank you very much for both speakers. Very interesting topics and very useful, I think, and practical to check from both angles, to check more for sensors and also from educational sides of artificial intelligence. So thank you very much. Thank you, Danny. Thank you, Vilija. Thank you, Dovydas, and all of you who's watching us on YouTube Live. And I want to also mention that we have a couple seats left in our Thursday meeting, non-official, just like gathering for Lithuanian AI Association members. So if you not registered, just go because we have limited amount of seats, and we check on Thursday. And for those who not attending on Thursday, we meet you on the next meeting in September. So thank you very much, everyone, and have a good evening.
Thank you.
Thank you, and labas vakaras. Yes, like that. Thank you.